Gentlemen, we've made it to episode 6, Free Fall, and now we finally know enough physics to actually explain the riddle that we've had at the beginning of the year, that objects of different mass actually fall with the same rate of acceleration. Now, why is that the case? The greater the mass of the object, true, the greater its force of attraction towards the Earth. But the greater the mass of the object, the smaller its tendency to move, the greater its inertia, the lazier the object is. So you increase the mass of the object, and yes, you increase its weight, and you would think that by increasing its weight that you would increase its acceleration. But the greater the mass of the object, the greater its inertia, and therefore its tendency to move is reduced. The effects cancel each other out, and the acceleration remains the same. Take a look at this diagram. On the left, you see an object falling with a mass m. And yes, when you have that mass m, you have a certain force on the object, which is F. F divided by m gives you the acceleration of the object, which we're going to call g. Let's say that you double the mass now. If you double the mass, yes, you do double the force on the object. You do double, here's one and here's the second one, you do double the force of gravity on the object, but you've also doubled the mass. You've doubled the object's resistance to motion. You've doubled the object's inertia. So double the mass doubles the force, but doubling the mass also doubles the inertia. The effects cancel each other out, and you're left with exactly the same acceleration, which is g. What is g equal to? We're talking about free fall, and in free fall, remember, free fall is falling under the influence of gravity alone. In free fall, acceleration we call g. It equals 10 meters per second squared. You see it right there. Technically, a more exact number would be 9.8 meters per second squared. It just makes things a little bit easier for the math if we say that g, the acceleration due to gravity, g is the acceleration due to gravity. If we say that g is 10 meters per second squared, that's the acceleration of an object in free fall, falling under the influence of gravity alone. No air resistance. In sum, when the acceleration is g, in other words, when you are in free fall, Newton's second law provides the explanation for the equal accelerations of freely falling objects of various masses. Newton's second law explains why if you drop a cannonball and a feather in a vacuum, they're both going to fall at the same rate or at the same acceleration. Cancel out air resistance. When the air resistance is negligible, there's an ACT word for you. Negligible means that you can assume the air resistance is nearly zero. Negligible means nearly zero. Then the acceleration is equal for all objects when they're falling close to the Earth's surface. So drop a feather and drop a cannonball in a vacuum. When you make air resistance negligible, you're going to fall with the same rate of change of velocity, with the same acceleration. Why? Because acceleration depends on force, the weight, and the inertia. Yes, the cannonball weighs much more than the feather. It's got much more force from gravity acting on it. But it also has a lot more inertia than the feather. The feather has hardly any inertia at all compared to the cannonball. And when you consider both force, when you consider both weight and inertia, when you consider both of them together, then you will understand that the acceleration is going to be equal when air resistance is negligible. Question time, just to see if you remember what free fall means. So at one instant, an object in free fall has a speed of 40 meters per second. Its speed 1 second later is what? Also 40 meters a second? Or 45 meters a second? Or 50 meters a second? Or none of the above? Pause the video now to select your answer. And the answer was, naturally, C, 50 meters a second. Why? The acceleration of an object in free fall is g. G is equal to 10 meters per second each second. And so after 1 second, you've added 10 meters a second in speed, and the speed ends up being 50 meters a second, assuming that the object is falling downwards. Next question, folks. A 5-kilogram iron ball and a 10-kilogram iron ball are dropped from rest. We're still in free fall. For negligible air resistance, negligible meaning hardly any, the acceleration of the heavier ball will be less or the same or more or undetermined. Pause the video and select your answer. And the answer was the same. For objects of different mass, acceleration is always the same. Yes, the 5-kilogram iron ball weighs less than the 10-kilogram iron ball, but the 10-kilogram iron ball has more mass, has double the mass of the 5-kilogram iron ball. Double the mass, double the inertia, and therefore it resists movement more than the 5-kilogram iron ball. The effects cancel each other out, giving you the same constant acceleration g, 10 meters per second each second. Last question now. You have the same two iron balls, the 5-kilogram and the 10-kilogram balls. You're dropping them from rest. When the free-falling 5-kilogram ball reaches a speed of 10 meters a second, the speed of the free-falling 10-kilogram ball is what? Less than 10 meters a second, 10 meters a second, more than 10 meters a second, or undetermined. Pause the video and select your answer. And the correct answer was B, 10 meters per second. The acceleration of both objects is a constant. It is the same, even though one weighs more than the other one. Why? Again, the inertia is greater for the object that weighs more. More inertia cancels out the greater weight. That's it for free fall, folks. In the last and final episode, we'll consider objects that do not fall in a vacuum when you have to consider air resistance. We call this real-life condition non-free fall.